Hi, Assalamualaikum to Dr. Hanif. We are from Group F. So today we are presenting the technique to study transition state in a reactions. So our group consists of 5 students, which is the first presenter is me, Atika, and the second presenter is Fazlina, third presenter is Aisha, and Amalin and also Ayuni are in charge to make this slide and also sharing the slide during presentation. So next slide. Going through the slide, there are two techniques will be shared. So the first one is high pressure NMR dynamic, and the second is first principle electronic structure calculations. Going to the first point, which is high pressure NMR dynamics, if we see the catalysis study in a long time scales, we can see that the enzymes show the conformational changes, and in modern structural biology have a revolution on our understanding on how the ground state structure provide a basis for working. And this thing is powered by three things, which is the first one is X-ray crystallography, and the second is electron microscopy, and third is nuclear magnetic resonance, which is known as NMR. And the importance of protein dynamics, which is especially interconversion between the ground states, it has become the important for catalysis, important also for the drug binding and also allosteric regulations. But to capturing the structure of transition states together at the same time, it becomes hindered because due to their intrinsic brevity. And the next explanation will be presented by Fazlina.
Okay, I will continue. About the high pressure NMR dynamic, the structural data coupled with kinetic isotope experiment have shown ability and probability as is with atomic detail of reaction restricted by the covalent bond transformation between them. However, despite their significance in defining movement within the protein energy landscape, the existence of TSCs for protein motion has precluded experimental observation. Such knowledge is important in order to understand of enzyme, as the basic concept of catalysis is to reduce the free energy required to transfer between reactant and product. Okay, in this NMR dynamic, we tend to analyze about the adenylate kinase. This enzyme has different pressure dependence. ADK's conformation shift was studied in parallel with pressure variable enzyme turnover and NMR relaxation dispersion experiment using homologs of ADK from mesophilic and piezophilic species. These species produce the adenylate kinase. For the conformation modification, meso ADK and piezo ADK both had substantially different pressure dependency, and the volumetric difference were rationalized in their TSS as differential solvation. Okay, for this slide, I would like to uh, look for the graph on the B first. Meso ADK is general pressure insensitive catalysis, while piezo ADK is pressure sensitive catalyst. Okay, then as we can see, it is visually independent from the pressure. The pressure doesn't affect how the enzyme regulate in this analysis. But for the piezo ADK, the pressure is, as we can see, the graph, it nearly double in the range of pressure uh, in this pressure. So for the graph for A, the we modified, we put meso ADK into the piezo ADK in order to generate a new modified enzyme. So that's all for high pressure NMR dynamic. Next, I will pass to Aisha about the second principle.
So the second technique is the first principle electronic structure calculation. So this principle will use the hybrid supermolecule polarizable continuum approach, and the result will be calculated. So the data will show the favorable transition state structure for the related process, for example, hydrolysis of formamide, which I will explain later, which it will form the intermediate structure formation. And from the calculated result, it will show the substituent effect on the transition state geometry and stabilization. Okay, so for example, for the hydrolysis of formamide, it will produce the formation of tetrahedral intermediate. And from the reported experimental, we can conclude that the favorable transition state structure may have three solvating water molecules remaining on the attacking hydroxide oxygen and two additional water molecules attached to the carbonate oxygen of formamide. So normally the result will demonstrate the substituent effect on the optimized transition state geometries, transition state stabilization, and we can calculate the free energy barriers for the decatalyzed hydrolysis of amides. So what is happening about the solvating water molecule? So when some or all of the hydrogen atom of formamide are replaced by the methyl group, the total number of water molecule hydrogen bonding will decrease from 3 for formamide to 2 for N-methyl acetamide and N-dimethyl formamide DMF and N-dimethyl acetamide DMA. So the data, from the data, we can conclude that the largest substituents of amide will hinder the solvent water molecule approaching the attacking hydroxide oxygen in the transition state. Therefore, it will destabilize the transition state structure and increase the free energy barrier. As the result, the DMA has the highest calculation, which is 26.0 kilocal per mole. So that's how we will determine the stabilization of the transition state structure, which we have two techniques. We have high pressure NMR dynamics, and the second one, we have the first principle electronic structure calculations. So that's all from us. Thank you for listening.